buried 100 meters underground. A 27-kilometer ring of superconducting magnets is smashing protons together at nearly the speed of light, billions of times per second. In that violence, CERN discovered something, a hidden structure woven into space itself, a load-bearing field running through every atom in your body right now, giving matter its mass, making chemistry possible, making you real. We are going inside the machine. We will trace the invisible glue holding every proton together, and we will follow the field that makes existence possible, all the way to a calculation that changed how physicists sleep at night. If you enjoy the journey, subscribe. Prepare yourselves. We begin. Deep beneath the border between France and Switzerland, sealed inside a ring of tunnels stretching 27 kilometers end to end and buried 100 meters below the surface, sits the largest machine humanity has ever built. From the outside, you would see nothing remarkable. A few concrete buildings scattered across fields near Geneva, some access roads, the occasional ventilation shaft rising from the earth, and yet directly beneath your feet, cooled to temperatures that make interstellar space seem warm, protons are racing at a speed that time itself cannot ignore. This machine is the Large Hadron Collider, and CERN built it for a single reason: to find out what the universe is made of, and what holds it together. That question sounds almost childlike, simple, satisfying to ask. And for most of human history, we assumed the answer was just a matter of zooming in close enough. Atoms, then electrons and nuclei, then protons and neutrons, then quarks, each level revealing smaller building blocks, like opening boxes to find smaller boxes inside. The assumption was that eventually, at some final level of smallness, we would find the last box, the irreducible thing, the bottom of reality. The Large Hadron Collider is our best attempt to crack that bottom open. It works by accelerating protons to a speed so close to the speed of light that the difference becomes almost philosophical. At full power, the protons complete the full 27-kilometer circuit about 11,000 times every second. Then, the beams are aimed at each other. The resulting collisions produce energies that existed in the first fractions of a second after the Big Bang, when the universe was younger than a heartbeat and hotter than anything that has existed since. At 4 specific points around the ring, enormous detector systems catch the wreckage. One of them weighs 14,000 tons. Another takes 40 million photographs per second. Together, they have recorded more collisions than there are grains of sand on every beach and desert on Earth. All of that engineering, all of those kilometers of superconducting magnets, all of that computational power pointed at one fundamental question: what is actually holding reality together? The machine delivered an answer that took 50 years of theoretical work to build toward. Something beautiful. And then, in the same breath, it revealed something that has been quietly unsettling the field ever since. The data was exactly right. That was the problem. What physicists discovered was a structure running through all of space, load-bearing, invisible, essential for the existence of every atom and every star. They found the scaffolding beneath reality. And then they ran the numbers on that scaffolding and found that it might be sitting in the wrong valley. Everything begins with cold. Before the Large Hadron Collider can accelerate a single proton, before a single collision can occur, the entire system must be brought to a temperature colder than the deepest void between the galaxies. The machine operates at -271.3 degrees Celsius. Outer space, the emptiest regions between star systems, hovers around -270 degrees. The collider is colder than that. It is, in that technical sense, the coldest large-scale environment in the observable universe. The reason is superconductivity. The magnets that steer the proton beams must carry enormous electrical currents without resistance. Any ordinary conductor heated even slightly would melt under the load. So CERN uses superconducting materials cooled with liquid helium, and those materials, at those temperatures, carry current with perfect efficiency. 124 miles of magnets, all held at a temperature that would be fatal to any biological system within seconds, all working in precise coordination to keep the beams on track. Now consider what is happening inside that cold ring. Each proton enters a chain of smaller accelerators before it ever reaches the main ring. By the time it arrives, it is already moving at a significant fraction of the speed of light. The main ring pushes it further. The final speed of each proton, at full collider power, reaches 99.99999991% of the speed of light. To picture that, a single proton, ordinarily a vanishingly small object with almost no kinetic energy at human scales, has been accelerated until it carries the energy of a flying mosquito. That energy compressed into something smaller than an atom. At that speed, time itself behaves differently for the particle. From the outside, where we stand, the proton screams around the circuit 11,000 times per second. The proton, if it could experience anything, would perceive the circuit taking only a tiny fraction of a microsecond. The particle exists in a separate temporal frame from the instrument holding it. Then the beams cross. Two beams, traveling in opposite directions, steered into a single point. The collision energy reaches 13.6 trillion electron volts. That is the energy density of the early universe, recreated in a space smaller than a proton, for a moment so brief no clock we can build can fully resolve it. 4 detector systems catch what comes out. The Atlas detector and the compact muon solenoid are built for general-purpose discovery. The experiment known as LHCb specializes in a specific class of particles and has become, over the years, the most productive exotic particle discovery engine in history. Alice watches the aftermath of heavy ion collisions, searching for the primordial state of matter that filled the universe before protons even formed. Together, by the end of 2025, these systems had processed the equivalent of 500 quadrillion collisions worth of data. And behind all of it sat the same foundational question: what rules does the universe actually run on? The closest thing we have to a complete answer is a theory so precise it borders on arrogance. A theory that has passed every test ever devised. A theory also missing something so fundamental that the gap should, by any reasonable standard, embarrass everyone. 50 years of work by hundreds of physicists across dozens of countries produced something almost miraculous. A single equation describing every known particle of matter and every known force except gravity. That equation is called the Standard Model Lagrangian. CERN sells it on a t-shirt. When people see it for the first time, they expect something monumental, some sprawling edifice of mathematics covering pages. Instead, they find something dense but compact, fitting comfortably in a single expression. And yet, from that expression, you can derive the structure of the atom, predict the behavior of radioactive decay, and calculate the precise magnetic properties of the electron to a precision that should not be possible. That last calculation is worth pausing on. The electron has a property called its magnetic moment. It measures how strongly the electron responds to a magnetic field. Quantum field theory, using the Standard Model, predicts the value of that magnetic moment to 1 part in a trillion. When experimentalists measure it, the number matches. That is the most accurate prediction in the history of science. Nothing else humans have ever built comes anywhere close. The theory was assembled piece by piece over decades. The quarks were proposed in the early 1960s as a way to make sense of the flood of new particles appearing in accelerators. The mathematical structure of the weak nuclear force was worked out through the 60s and 70s. The gluon, carrier of the strong force, was confirmed experimentally in 1979. The Higgs boson, the final predicted piece, was discovered in 2012. The puzzle took half a century and the contributions of physicists on every continent. What the theory gives us is a complete inventory of the visible world. Every atom in your body, every photon entering your eye, every reaction in every stellar core across the galaxy, governed by combinations of 17 particles interacting through 3 forces. The periodic table of elements, all the chemistry of biology, all the nuclear physics powering every star in the sky, it all emerges from this single framework. The Standard Model is the most successful intellectual achievement in human history. It is also incomplete in a way that should be impossible to ignore. Every prediction it makes with extraordinary accuracy. But accuracy and completeness are different things. There are things in the universe for which the Standard Model has no language, no particles to assign, no equations to capture. Those gaps are enormous. They cover most of the universe by mass. But before getting to what the theory misses, the 17 particles it did find deserve a proper introduction. They are a cast of characters, and the dread that arrives later depends entirely on understanding which particle is doing what. Picture the universe as a performance built from a very small cast. Everything you have ever seen, touched, or measured reduces to 17 fundamental players. Learning their roles matters because what comes later depends on knowing exactly which particle is doing what. The first category is matter. Matter particles are called fermions, and they come in 2 families. The first family is quarks. There are 6 of them, bearing the names up, down, charm, strange, top, and bottom. Up and down quarks build the protons and neutrons inside every atomic nucleus you will ever encounter. Each quark carries a property called color charge, a quantum number governing how quarks interact with the strong force. The name has nothing to do with visible color. The second family of matter particles is leptons, 6 of them as well. The most familiar is the electron, the particle orbiting every atomic nucleus, responsible for all of chemistry and electricity. Its heavier cousins, the muon and the tau particle, behave like electrons but weigh far more. Then there are 3 neutrinos, one for each of the charged leptons, nearly massless and passing through ordinary matter as though it does not exist. 12 matter particles in total. The remaining 5 are force carriers, called bosons. The photon carries electromagnetism, the force governing light, chemical bonds, and every electrical phenomenon you have ever encountered. The W bosons and the Z boson carry the weak nuclear force, the one responsible for radioactive decay and for the reactions fueling stellar cores. The gluon carries the strong nuclear force, binding quarks inside protons and neutrons. And then there is the 17th particle. The Higgs boson is different from every other particle in this cast. The other particles are matter or force carriers. The Higgs boson is neither, exactly. It is a ripple in a field, a disturbance in something that fills all of space at a constant value, something whose existence is a prerequisite for atoms to work at all. The Higgs boson is more than a particle. It is evidence of a hidden structure. We will come back to that structure, because it is where the story takes its first, genuinely unsettling turn. But the cast list has a gap that the Standard Model has never managed to fill. 3 forces are described. The 4th force, gravity, is missing entirely. The Standard Model has nothing to say about gravity. The 2 greatest frameworks in physics, the Standard Model and general relativity, the theory of how mass curves space-time, cannot be merged. Every attempt breaks down in the mathematics. 2 theories, each describing the universe with extraordinary accuracy, and they are fundamentally irreconcilable. That gap is significant. What it signals, together with several other failures soon to come, is that the Standard Model is a placeholder, a remarkably accurate placeholder, the most accurate placeholder imaginable, but a placeholder nonetheless. The question is, a placeholder? For what? Because what the theory cannot see would, if you could see it, fill the universe, for all its extraordinary precision. The standard model describes only 5% of the universe. That number lands wrong when you first hear it. The most accurate theory in the history of science, the framework that passes every experimental test ever devised, the equation physicists call their greatest triumph, accounts for 5% of what exists. The other 95% has no description, no particles assigned to it, no place in the theory at all. Around 27% of the universe's total energy density is dark matter. We know it exists because galaxies rotate incorrectly. Without additional mass holding them together, the outer stars in a spiral galaxy would be moving fast enough to fly off into space. They do not fly off. Something invisible is binding them. That invisible something is dark matter, and it outweighs all visible stars and gas and dust by roughly 5-to-1. The standard model has nothing to say about it. There is no dark matter particle in the theory. There are no dark matter interactions. There is no mechanism, just a blank space where 27% of the universe should be. The remaining 68% is dark energy, a pressure woven into the fabric of space itself that is driving the universe to expand faster and faster as time goes on. The standard model does attempt to predict the energy density of empty space, and it produces a number. The problem is that the number is off from what we actually measure by a factor that has 120 zeros after it. Physicists call this the worst prediction in the history of science. And then there is the matter-antimatter problem. The Big Bang produced matter and antimatter in equal quantities. When matter meets antimatter, both annihilate into pure energy. So the universe's first moments should have been a self-erasing catastrophe, the entire contents of reality cancelling itself out, leaving nothing but a cold sea of photons with no structure, no atoms, nothing at all. We are here, which means something tipped the scales. The standard model does contain a mechanism for preferring matter over antimatter, but it is too weak by many billions of times to explain the imbalance we observe. By a factor of billions, the theory falls short of explaining our existence. These are the failures at the cosmic scale. They are real, they are enormous, and physicists know about every one of them. But the most immediately unsettling problem sits closer. It sits inside a proton. It has to do with what you are actually made of at the most fundamental level you can reach with current physics, and the answer reveals that almost everything you call mass has nothing to do with the mass of particles at all. Inside every proton in your body, something extraordinary has been happening continuously since the first protons condensed from the cooling plasma of the early universe. A proton contains 3 quarks. Most people carry around a picture of a small sphere with 3 smaller spheres packed inside it. That picture is wrong in almost every important way. A proton is a cage. The bars of that cage are made of something unlike anything else in physics, and the cage has a remarkable property. The harder you pull on it, the stronger it gets. The strong nuclear force binds quarks together through particles called gluons. Gluons carry what physicists call color charge, borrowing color as a metaphor for the quantum property that makes the strong force work. 3 quarks inside a proton each carry a different color charge, and the combination of all 3 is color neutral, stable, self-contained. The proton holds together. What makes the strong force unique is what it does when you try to pull the quarks apart. Every other force in physics weakens with distance. Gravity falls off, electromagnetism falls off. The strong force does the opposite. Pull 2 quarks apart, and the gluon field between them does not weaken. It stretches, storing energy as it goes, like a rubber band under increasing tension. Except instead of a breaking point, something stranger waits. When enough energy accumulates in the stretched field, the field does not simply snap and release the quarks. It uses the stored energy to create new quarks from the vacuum itself. You end up with more particles, still bound, never free. This is confinement, and it is absolute. A single free quark has never been observed in any laboratory in the history of physics, and the theory of the strong force predicts that one never will be. Pull with whatever energy the universe permits, and the strong force will produce more bound particles before it permits a free quark to exist alone. The more prisoners you create. This means the strong force is building an unbreakable cage, one that has held since the first fraction of a second of the universe's existence and will hold until the last proton decays, billions upon billions of years from now. Your body is threaded with these cages. Every atom in everything you can see is threaded with them. The cage itself, though, hides something about what mass actually is and where it actually comes from. The answer overturns the most basic assumption most people carry about the substance of their own bodies. Weigh a proton and you get a specific number: 938 million electron volts. That number is solid, reproducible, one of the most precisely measured quantities in physics. Then weigh the 3 quarks inside it. The Higgs field, the structure filling all of space, gives each quark a small but genuine mass through coupling. An up quark receives roughly 2 million electron volts from the Higgs. A down quark gets around 5 million. These are real masses, produced by a real physical interaction. The Higgs mechanism works exactly as the theory describes. Add those 3 quark masses together and you get somewhere around 11 million electron volts. The proton weighs 85 times more than the particles it contains. The missing mass is the energy of the gluon field thrashing inside the proton. It is the kinetic energy of quarks racing at near light speed inside a volume smaller than the wavelength of visible light. It is the tension stored in the color-charged medium holding the whole structure together. Energy and mass are the same thing expressed differently, and the proton's apparent weight is almost entirely the energy cost of confinement. The periodic table of elements, every molecule, every biological structure in your body, all of it rests on this same architecture. A small mass from the Higgs field, dwarfed entirely by the stored energy of gluon fields holding quarks in their cages. Everything you think of as solid matter is mostly trapped field energy expressing itself as weight. The chair you are sitting on is mostly the energy cost of imprisoning quarks. The weight of your own hand is the energy required to hold those quarks from reaching a freedom they can never achieve. Solid matter dissolves under scrutiny. Organized, imprisoned field energy wears the costume of substance all the way down. Mass, at the deepest level physics can currently reach, is a derived quantity. It emerges from the geometry of confinement and from the background fields permeating space. The Higgs contributes a small fraction. The gluon cage contributes almost everything else. The field does the heavy lifting, which raises a question that will grow stranger the further we go. If mass is mostly stored field energy inside the proton, then what exactly is the field sitting in? What is the vacuum inside a proton, the space between the quarks, actually made of? The answer involves something that should not be there at all. Beneath what we call particles, beneath even the gluon fields and the quarks they bind, there is something that physicists call the quantum vacuum. And the quantum vacuum is one of the most misleading names in science. Vacuum implies emptiness, the base state, the floor below everything, the nothing from which all somethings arise. This is what most people picture when they imagine outer space, or the gap between electrons and nuclei inside an atom, or the space between particles in a proton. Nothing. The reality hiding under that word is something else entirely. The quantum vacuum of the strong force is a seething, structured medium. It is populated by virtual quark-antiquark pairs that constantly form and dissolve, their existence borrowed from the vacuum's own energy budget and repaid before any detector can catch them. These pairs do not cancel to nothing. Their collective behavior, averaged across all of space, produces a quantity called the chiral condensate, a non-zero value that permeates the vacuum everywhere, at every point, always. That condensate is doing active physical work. It is responsible for the masses of the light mesons, the particles built from a quark and an antiquark, which are the most common byproducts of strong force interactions. If the vacuum were truly empty, if those virtual pairs were absent, the masses of those particles would be completely different, and the resulting changes to nuclear physics would cascade upward into a universe that could not sustain complex atomic structure. The vacuum is load-bearing. Its structure, rather than any solidity, is what holds things up. Something else lives in the vacuum as well. Topological structures called instantons. These are events where the quantum fields of the strong force tunnel briefly between different configurations, flickering through states that are mathematically distinct but connected by quantum mechanics. They are invisible to direct measurement, but their effects appear in the masses and interactions of particles throughout the strong force spectrum. The quantum chromodynamics vacuum is, in a precise technical sense, a physical medium. It has energy, it has condensates, it has topology, and its specific structure is why matter can exist in organized forms. Every point in space, including inside you, is threaded with this structured medium. The strong force vacuum is scaffolding, but the strong force vacuum is only one layer of the hidden architecture. There is another field, running through all of space at a constant non-zero value, where the quantum chromodynamics vacuum fills the interior of particles and manifests as mass through confinement. This other field operates everywhere without exception, including in the emptiest reaches of intergalactic space, including between the atoms in your hand. Without it, every electron in the universe becomes massless. Atoms dissolve, chemistry ends. The universe becomes an undifferentiated plasma with no structure and no future, running through every point in the observable universe, at this moment, and at every moment since a fraction of a second after the Big Bang, is a field with no direction and no visible presence. A field that interacts with particles by giving them the property that makes complex matter possible. This is the Higgs field. It is the most consequential hidden structure in physics. Every other force field you can name reaches out and acts on things. The gravitational field pulls masses together. The electromagnetic field pushes and pulls charges. The strong force binds quarks. These forces reach out across space and cause change. The Higgs field does something different. It sits at a constant value at every point in space, and particles moving through it experience a kind of coupling that translates directly into mass. The value the Higgs field holds, everywhere, always, corresponds to 246 billion electron volts. That value is called its vacuum expectation value, and it is universal, the same in the core of a galaxy as it is in the space between your atoms. Particles that couple strongly to the field acquire more mass. Particles that couple weakly acquire less. The electron couples moderately and ends up light enough to be captured by atomic nuclei. The top quark couples with extraordinary strength and becomes the heaviest known fundamental particle, nearly 200 times heavier than a proton. Particles that do not couple to the Higgs field at all, like the photon and the gluon, remain massless and travel at the speed of light forever. Remove the Higgs field, and this entire hierarchy collapses. Electrons become massless. Massless electrons cannot be captured into stable orbits around nuclei. Without that capture, atoms cannot form. Without atoms, there is no periodic table, no chemistry, no biology, no organized complexity of any kind. The stars in the sky burn through a chain of nuclear reactions that depend on the weak nuclear force operating at a specific range, a range set by the masses of the W and Z bosons. masses provided entirely by the Higgs field. The entire architecture of the universe, from the fusion rates of stellar cores to the protein folding in your cells, rests on this one field holding its value. The Higgs field is the foundation of physics. The particle discovered at CERN in 2012 was a ripple in this field, a brief disturbance caused by injecting enough energy into a small region of space to knock the field off its equilibrium value for a moment. Catching that ripple took the most powerful accelerator ever built and 2 independent detector collaborations working for decades. Finding it was the culmination of 50 years of theoretical work and experimental preparation. And then the physicists who found it ran the numbers. They took that measurement, 125 billion electron volts, and they calculated what it meant for the shape of the Higgs field's energy landscape, for the stability of the structure underlying everything. What they found has not stopped disturbing them since. On the 4th of July, 2012, a room full of physicists at CERN broke into applause, and Peter Higgs, the theoretical physicist who had proposed the field half a century earlier, sat in the audience and wept. The announcement was made jointly by 2 independent detector teams, Atlas and the compact muon solenoid. Both had found the same signal, a new particle at a mass of approximately 125 billion electron volts, appearing in the collision debris with a statistical confidence exceeding 5 standard deviations, the threshold particle physics uses as the formal standard for discovery. This was the Higgs boson, the final piece. The room understood what had just happened. 5 decades of theoretical work confirmed. The mechanism responsible for the mass of matter proven real. The standard model completed. The celebrations were genuine and fully deserved. Physicists who had spent entire careers working toward this moment finally had their answer. The Higgs was real. The field was real. Everything the theory had built on that foundation was real. Then the calculators came out. The Higgs boson mass is a specific number, 125.09 billion electron volts, as later measurements refined it. That precision matters enormously. The Higgs mass carries weight far beyond a single particle's character. It is an input into equations describing the stability of the quantum field filling all of space. Physicists who study quantum field theory know that the Higgs field has an energy landscape. Like a ball resting at the bottom of a bowl, the field sits at its lowest available energy state. The shape of that bowl depends on parameters that include the Higgs boson mass. Measure the mass precisely enough and you can calculate the shape of the bowl. Measure it precisely enough and you can determine whether the bottom of the bowl is the actual bottom or whether there is a deeper valley somewhere below, separated from our current state by an enormous barrier. So the calculation was done. The new measurement, combined with the known mass of the top quark, the heaviest particle and the one most strongly coupled to the Higgs, fed into the stability equations. The result came back as something subtler than alarm, a slow, specific, technical unease. The kind that settles in when a number you just measured turns out to be sitting very close to a boundary you hoped it would not be near. The discovery that should have closed the chapter had opened something else. Instead, after the celebrations quieted and the precision measurements began, a different question moved to the front of the field. The Higgs mass of 125 billion electron volts was confirmed, and that specific value is one of the most consequential numbers in physics. Its placement raises a problem the standard model has no answer for, and the problem has been sitting at the center of theoretical physics for 4 decades. In quantum field theory, particles do not sit in a passive vacuum. The space around any particle seethes with virtual particles, constantly appearing and disappearing in quantum loops, forming and annihilating too briefly to observe directly, but real enough to affect the properties of everything around them. These virtual loops contribute quantum corrections to particle masses. For most particles, these corrections are modest and manageable. For the Higgs boson, they are catastrophic. The Higgs mass receives corrections that grow with the square of whatever energy scale the theory eventually breaks down at. If the standard model holds all the way up to the energy scale where quantum gravity becomes relevant, roughly 10 trillion electron volts, then the natural expectation for the Higgs mass is somewhere in that enormous range. Far larger than anything detectable by any conceivable collider. The measured Higgs mass is 125 billion electron volts. To reach the observed value from the natural expectation, the enormous quantum corrections must cancel against each other to an extraordinary precision. The cancellation must be exact to 34 decimal places. The standard model requires this cancellation but provides no mechanism to explain it. It is as though you built a tower 10 million stories tall, and a basement of exactly equal weight appeared beneath it, perfectly counteracting the load for no reason the architecture can account for. The balance is measured. The reason for the balance is absent. This is the hierarchy problem, and it is the most embarrassing unexplained coincidence in physics. For 4 decades, a solution existed. Physicists had a theory, elegant and mathematically compelling, that predicted the hierarchy problem would resolve itself naturally. The theory made specific predictions about new particles that the Large Hadron Collider, once built, would find at accessible energies. The solution had been waiting, fully formed, since the 1980s. It had a name: supersymmetry. Supersymmetry predicts that every known particle has a partner particle with opposite quantum properties. Those partners, if they exist, would enter the quantum loops that give the Higgs its enormous corrections. And crucially, the partners' contributions would cancel the corrections from the known particles, almost perfectly, stabilizing the Higgs mass at the small value we observe. The cancellation would be automatic, built into the structure of the theory, requiring no unexplained fine-tuning at all. The mathematics worked beautifully. Theorists who worked through the predictions found that the supersymmetric partner particles should appear somewhere in the energy range the Large Hadron Collider was designed to reach. Building the collider would effectively be building a supersymmetry detector. If the theory was right, the partners would show up. The hierarchy problem would dissolve. The scaffolding holding the universe together would have an explanation. The collider was built. The energy was reached. The collisions are happening right now. The predicted particles have not appeared. Supersymmetry was the most elegant solution physics had ever produced for a problem that had no elegant solutions. The theory arrived in the parents' early 1970s, emerged from the mathematics of particle physics, and within a decade had become the dominant framework for addressing the hierarchy problem. Its central proposition was simple. Every particle in the standard model has a partner. Quarks have squarks, electrons have selectrons, gluons have gluinos. The partners carry opposite quantum spin statistics from their counterparts. That spin difference is the point. Quantum corrections to the Higgs mass come in 2 types depending on whether the contributing particle is a fermion or a boson. Fermion corrections push the Higgs mass in one direction. Boson corrections push it the other. In the standard model, these corrections do not cancel, so the Higgs mass receives enormous positive shifts that must be tuned away by hand. In a supersymmetric theory, every known fermion has a bosonic partner, and every known boson has a fermionic partner, and the contributions from each pair cancel automatically. The hierarchy problem dissolves. The Higgs mass stays small without requiring any unexplained fine-tuning. The mathematics worked. Physicists spent 4 decades building variations of the theory, extending it, exploring its predictions, checking its internal consistency. Supersymmetric theories also offered a bonus. The lightest supersymmetric partner particle could not decay into standard model particles, which made it stable, invisible, and exactly the right kind of candidate for dark matter. A single theory addressed 2 of the biggest unsolved problems in physics simultaneously. By the time the Large Hadron Collider was being designed, Supersymmetry had been the dominant proposed solution to the hierarchy problem for so long that the collider's discovery reach was shaped partly by its predictions. If supersymmetric partners existed at the energies where the hierarchy problem demanded they appear, the collider would find them. The squarks and gluinos, the partner particles of the quarks and gluons, should appear in collisions at energies well within the machine's range. Run 1 began in 2010. Proton-proton collisions at 7 trillion electron volts, the highest energy ever achieved in a laboratory. Both the Atlas detector and the compact muon solenoid looked for the signatures of supersymmetric particles, specific patterns of missing energy, characteristic decay chains, distinctive combinations of visible particles in the detector. The data arrived in enormous quantities. Analysis teams sifted through it with algorithms trained on the predicted signatures. Nothing. Run 2 raised the collision energy to 13 trillion electron volts and ran from 2015 to 2018. More data, higher energies, better analysis techniques, refined predictions. The search is expanded to cover variations of the theory with different mass spectra, different decay modes, different partner particle hierarchies. Nothing. Run 3, beginning in 2022, reached 13.6 trillion electron volts with the highest collision rates in the machine's history. The gluino mass exclusion reached 2.2 trillion electron volts. Squarks were excluded up to nearly 2 trillion electron volts. Nearly every accessible version of the theory was searched directly. The silence remained unbroken. In 15 years of operation at the highest energies humans have ever achieved, the Large Hadron Collider has found no supersymmetric particles. The statistical confidence in that absence is overwhelming. The machine looked everywhere the theory said to look. The predicted partners are not there. The solution that was supposed to explain why the scaffolding sits where it does never showed up, and that absence is itself a result that demands an explanation. By the time Run 2 results were fully analyzed, physicists no longer softened the language. The simplest versions of supersymmetry, the models that addressed the hierarchy problem most directly, were effectively excluded by the data. The very feature that had made supersymmetry compelling for 4 decades. The prediction that partner particles would appear at energies where the Higgs mass becomes unnatural without them had become the source of its difficulty. The logic runs like this. The hierarchy problem demands that any stabilizing new physics appear close to the electroweak scale, the energy range where the Higgs field operates. If the supersymmetric partners are too heavy, they cannot efficiently cancel the quantum corrections to the Higgs mass. The cancellation becomes imprecise, and some degree of fine-tuning returns through the side door. The theory stops solving the problem it was invented to solve. Every time the Large Hadron Collider failed to find a gluino and raised the exclusion limit, the required fine-tuning in the surviving supersymmetric models increased. Variants of the theory can be constructed that evade the current exclusions by placing partner particles above the accessible range or by making their decay signatures difficult to see in the detector. Those variants exist. They have not been excluded, but working within those frameworks requires accepting that supersymmetry does not, after all, solve the hierarchy problem naturally. It either requires its own fine-tuning, or it operates at energies beyond any machine we are likely to build in this century. A 2025 review paper, surveying the full scope of the null results, framed it plainly. The simplest supersymmetric models are excluded. The remaining variants survive by becoming something other than the original solution, so the hierarchy problem stands. The Higgs mass of 125 billion electron volts has no explanation in the standard model, and the leading candidate explanation has no experimental support. Other solutions exist on paper. Theories proposing extraspatial dimensions where gravity leaks into directions imperceptible at low energies, which would lower the effective Planck scale and make the fine-tuning less severe. composite Higgs models, where the Higgs is a bound state of even more fundamental particles, analogous to how pions emerge from quark-gluon dynamics. Cosmological selection mechanisms, where the universe's history drives parameters towards specific values. The multiverse, where the Higgs mass has whatever value it does, because we exist in one of many universes, where the value permits complex matter and the others contain no one to notice. Each of these carries problems. The extra dimension models produce specific signatures at the collider that have not appeared. Composite Higgs models struggle against the precision measurements that the Higgs passes exactly. Cosmological mechanisms are difficult to test. The multiverse interpretation makes no prediction that any experiment could verify or refute. The silence from the main detectors carries definite weight. In particle physics, when a machine achieves sufficient energy and sensitivity, the absence of a signal is evidence of absence. The Large Hadron Collider has achieved sufficient energy and sensitivity. It has been looking for 4 decades worth of promised particles. While the theorists wrestle with what the silence means, a different detector at the same machine has been producing a very different kind of result. Something is showing up. Lots of somethings. 80 of them so far. While the hierarchy problem accumulated unresolved theoretical debt, the experiment known as LHCb was quietly producing one of the most productive particle discovery runs in the history of physics. The detector is designed for a specific purpose. Watching the narrow forward cone of collision debris angled along the beamline 40 million times per second, with a specialization in a class of particles called beauty hadrons. These are heavy objects containing bottom quarks that decay through a chain of steps and carry information about the boundaries of known physics and their decay patterns. What LHCb was also doing, as a consequence of watching beauty hadron decays with extraordinary precision, was cataloging what emerged from those decays. What emerged included something that had been theoretically predicted for 6 decades, observed as faint hints in various experiments over the years, and never confirmed to the standards the field requires. Particles built from quark configurations the textbooks acknowledged were possible, but had never definitively been seen. In the original 1964 paper proposing the quark model, the physicist Murray Gell-Mann noted, almost in passing, that the framework permitted more than the 2-quark and 3-quark combinations that would become known as mesons and baryons. Quarks could, in principle, combine in larger groups if the total quantum numbers worked out. He mentioned it and moved on. He had enough to establish without exploring every corner of the framework he was building. 60 years later, LHCb began finding those corners. As of the announcement made at the Rencontres de Morient conference in March 2026, 80 new hadrons had been discovered across all Large Hadron Collider experiments. 24 of them are exotic, particles whose quark content cannot be explained by conventional 2-quark or 3-quark models. 21 of those 24 exotic hadrons were found at LHCb. The pace of discovery has been remarkable. In a period spanning roughly a decade, the detector confirmed particles containing 4 quarks bound together in a single state, particles containing 5 quarks, particles combining quark types that never appear together in ordinary matter, and particles sitting so close to the threshold of dissolution that their existence strains intuition. Each one met the statistical standards the field imposes, reproducible across independent analysis teams working on the same dataset. To understand why this matters requires stepping back from the individual particles and thinking about what the catalog is mapping. Quantum. Chromodynamics is correct in all the regimes where its equations can be solved. The problem is that the equations become intractable in exactly the regime where exotic particles form. The theory is right, but computing its precise predictions for complex quark configurations requires methods that go beyond what current mathematics can handle directly. The exotic hadrons are therefore experimental probes. Each confirmed particle constrains the models attempting to handle the strong force in this complex regime. Each measured mass and lifetime rules out some theoretical pictures and supports others. The particle zoo that confused physicists in the 1950s and eventually revealed the quark model hiding beneath it may be doing something similar now. At a deeper level, the first exotic discovery came as a particular shock: 2 quark combinations, 3 quark combinations. These were the building blocks that organized the particle physics of the 20th century. Mesons held a quark and an antiquark. Baryons held 3 quarks. The proton had 3. The neutron had 3. The pion, the particle mediating forces inside atomic nuclei, held 2. The entire menagerie of particles discovered in the mid-20th century resolved into these 2 categories once the quark model arrived. The question of whether 5 quarks could hold together in a single bound state had been technically open since Gell-Mann's 1964 paper, but practically speaking it sat in a drawer. Claims surfaced occasionally and retracted under scrutiny. The consensus drifted toward treating pentaquarks as theoretical curiosities that happened not to appear in nature. In 2015, LHCb opened that drawer and found something inside it. The signal appeared in the decay products of a particle called the lambda B0 baryon, a 3-quark state containing a bottom quark. When the lambda B0 decays, it produces a J-psi meson and a proton among other products. J-psi mesons are themselves particles containing a charm quark and a charm antiquark. The LHCb analysis team was studying the distribution of masses in this decay system, looking at how the J-psi and the proton combine, when 2 structures appeared in the data that had no explanation in any conventional 2-quark or 3-quark framework. The structures were pentaquarks. 5 quarks bound together, 2 up quarks, 1 down quark, 1 charm quark, and 1 charm antiquark, all held inside a single confinement structure by the strong force. Their existence was confirmed at a statistical significance exceeding 9 standard deviations, well beyond any reasonable threshold for doubt. The discovery was a proof of principle as much as a new entry in the catalogue. The strong force can build stable configurations of 5 quarks. Confinement, the mechanism that prevents free quarks from existing, operates just as powerfully on these more complex structures as on conventional 3-quark baryons. The rules of quantum chromodynamics permit a much wider range of stable configurations than the textbooks had been presenting. A larger dataset from Run 2 later resolved the 2 pentaquark states into 3 distinct states with sharper masses, confirming the structures and adding detail to their properties. Each confirmation added precision to the constraints on theoretical models attempting to describe them. What the pentaquarks could not resolve, at the time of their discovery, was the question of their internal structure. A 5-quark state could be tightly bound, with all 5 quarks confined together in something like a single composite particle. Or it could be more loosely organized, behaving like 2 conventional particles orbiting each other at close range, held by the residual strong force between composite objects rather than by direct quark-gluon confinement. Both possibilities were consistent with the early data. Distinguishing between them required better measurements and more exotic examples. LHCb provided both. And then it found a 5-quark state with even stranger ingredients inside it. 3 new exotic particles announced in a single presentation. That had never happened before. At a seminar held at CERN in 2022, the LHCb collaboration presented results from their Run 2 dataset that pushed the exotic hadron catalog into genuinely new territory. The announcement came in 3 parts, and each described a particle with properties that would have seemed implausible a decade earlier. The first was a pentaquark containing a strange quark alongside a charm-antiquark pair and 2 light quarks. Strange quarks appear in some conventional hadrons, the class known as strange particles that were among the first to confuse physicists in the 1950s. A pentaquark with strangeness had never been confirmed. This one appeared at a mass of approximately 4,459 million electron volts and was confirmed at a statistical significance of 15 standard deviations. 15. The field uses 5 as its formal threshold for discovery. 15 is a result with essentially no remaining ambiguity. The second and third results were tetraquarks, 4-quark states, but tetraquarks of a specific kind that had never been seen before. Open-charm tetraquarks with electric charge differing by 2 units from 0. This requires a moment to appreciate. Conventional hadrons carry electric charges of 0, +1, or -1. Protons carry +1, neutrons carry 0. Pions can carry +1, -1, or 0. The charge is determined by the quark content and the arithmetic of quark charges. Up quarks carry 2/3 of the elementary charge. Down quarks carry -1/3. To build a particle with total electric charge of +2 requires an unusual combination of quarks. The doubly charged tetraquark achieved this. Its existence violates no physical law, but it sits in a region of quark combination space that had simply never been reached before. The conventional hadron framework cannot produce a particle with this charge from 2-quark or 3-quark combinations. This particle exists because the strong force is willing to bind 4 quarks in a specific arrangement that produces a total charge conventional hadrons cannot carry. A physicist serving as LHCb physics coordinator compared the period to the 1950s, when the cascade of unexpected new particles arriving in accelerator data eventually forced the field to recognize that quarks were the hidden layer of structure underneath. The current cascade may be pointing at something similarly fundamental, a new level of understanding about how confinement actually operates in complex quark systems. The comparison is deliberate. The pattern of exotic states being discovered, their masses, their lifetimes, and which quark combinations appear stable, all of this is building a map of territory that quantum chromodynamics predicts but cannot yet analytically describe. The experimental results are running ahead of the theory's ability to compute. One particle in the catalogue set a record that separated it from everything that came before. Among all the exotic hadrons catalogued by LHCb and its experimental partners, one sits in a position so precarious it seems less like a particle and more like an argument for the existence of something that should dissolve on contact. The doubly charmed tetraquark, designated as the TCC+, was announced in 2021. Its quark content is 2 charm quarks and 2 light antiquarks. Charm quarks are heavy, roughly 1,300 times the mass of an up quark, and their presence inside a tetraquark gives the system a mass and character quite different from the lighter exotic states discovered earlier. The feature distinguishing this particle from everything else in the exotic hadron catalogue is its placement relative to a specific threshold. There is an energy level at which a tetraquark made of 2 charm quarks should spontaneously fall apart into 2 separate mesons, each carrying 1 charm quark. Below that threshold, the particle persists. At that threshold, dissolution becomes energetically neutral. Above it, the particle becomes unstable. The TCC+ sits 360,000 electron volts below the threshold. 360,000 electron volts sounds like a significant buffer until you compare it to the particle's total mass, which is in the range of 3,875 million electron volts. The gap between this particle and the point where it should dissolve is roughly 1 part in 10,000 of its total mass. At this proximity to the threshold, theorists began proposing that the particle is less a conventional tetraquark. With all 4 quarks tightly bound in a single confinement structure, and more a loosely coupled hadronic molecule, 2 separate charm-containing mesons so close in space that the residual strong force between them holds the pair together without any single gluon cage enclosing all 4 quarks. The 2 mesons hover near each other, like 2 bubbles that have not quite merged, kept together by forces operating between composite objects rather than between individual quarks. If that interpretation is correct, the TCC+ represents a new category of bound state in quantum chromodynamics, one that the original quark model had no framework for, and one that expands the range of configurations the strong force can maintain at the edge of dissolution. The particle also earned another record. It is the narrowest exotic hadron ever observed. Its decay width, the quantum mechanical measure of how quickly it dissolves, is smaller than any other confirmed exotic state. The TCC+ barely exists by the standards of particle physics. It clings to stability by a margin almost too thin to measure. Its existence proves that the strong force can operate at the very edge of this kind of stability, holding structures together that should in principle fall apart, doing so through subtler residual forces between particles that already carry confined quarks inside them. The next question was whether the strong force could do something even more unusual: bind 4 quarks together when all 4 of them are the heaviest kind. Somewhere in the collision debris that LHCb and its counterparts process by the trillion, a specific signal appeared in 2020 that had never been seen in any experiment, a particle made entirely of charm quarks. The fully charmed tetraquark contains 2 charm quarks and 2 charm antiquarks. No light quarks, no strange quarks. 4 of the heaviest quarks that appear in bound hadrons, all confined together inside a single particle whose mass is nearly 7 times that of a proton. Charm quarks do not appear in ordinary matter at any temperature found in the natural universe today. They were abundant in the first microseconds after the Big Bang, before the universe had cooled enough for them to decay into lighter particles. In the present universe, charm quarks exist only briefly, produced in high-energy particle collisions or when cosmic rays strike the upper atmosphere. Any composite particle built entirely from charm quarks is therefore absent from the visible matter of stars, planets, and living things. This particle appeared in the spectrum of secondary particles produced when 2 photons from the collision debris interact. 2 independent analysis teams, one from LHCb and one from the Compact Muon Solenoid collaboration, saw the structure. The Atlas collaboration later confirmed it as well. 3 independent experiments, each analyzing different aspects of the same class of collisions, all found the same signal at the same mass. Additional structures appeared nearby in the mass spectrum. Further fully charmed states at different masses hinted at a spectroscopy of all heavy quark matter, a family of particles built from the same charm quark ingredients arranged in different configurations, each with a distinct mass and set of quantum numbers. Physicists who study hadron spectroscopy recognize the pattern. When a new kind of bound state is discovered, it rarely comes alone. The rules of the underlying theory that permit one combination typically permit related ones, and the mass spectrum begins to populate. The fully charmed tetraquark family represents the upper extreme of the exotic hadron catalog. Pentaquarks demonstrated that 5 quarks could share confinement. Doubly charged tetraquarks demonstrated that exotic charge combinations were accessible. The all-charm tetraquark demonstrated that even the heaviest stable quark type could form exotic configurations without any lighter quarks to assist. Each new corner of the catalog pushed the experimental map further into post territory that quantum chromodynamics had predicted in principle but had never been asked to describe in practice. The most recent entry in that catalog arrived just weeks before this script was written, and it resolved a mystery that had been waiting 20 years. 20 years is a long time in particle physics. Experiments change, accelerators shut down and are replaced, entire research programs shift focus. So when a measurement made in 2002 returned to haunt the field in 2026, it required a certain kind of patience to follow. In 2002, the Fermilab Accelerator Laboratory in Illinois detected a faint signal that appeared to suggest the existence of a particle containing 2 charm quarks. This class of particles is called doubly charmed baryons. A conventional baryon contains 3 quarks, A doubly charmed baryon contains 2 charm quarks and 1 lighter quark. The Fermilab measurement was intriguing but problematic. The mass it reported did not match the predictions of theory. Physicists could not reconcile the signal with the calculations, and no other experiment confirmed it. The result sat in an uncomfortable middle state for 2 decades, neither confirmed nor definitively refuted. The upgraded LHCb detector, installed in 2023 after long shutdown 2, began collecting data at unprecedented rates. By 2026, a specific analysis team had accumulated enough collision events involving doubly charmed baryon candidates to push the statistical significance to 7 standard deviations. The particle was real. Its mass came in at 3,620 million electron volts. That mass matched the theoretical predictions. It also matched the mass predicted by comparison with the related particle that LHCb had confirmed in 2017, the doubly charmed baryon carrying 2 positive charges rather than 1. The 20-year-old discrepancy from the Fermilab measurement dissolved. Either the earlier signal had been a statistical fluctuation, or its mass had been measured with insufficient precision. Either way, the new result was unambiguous. This particle, the CCC+ baryon, became the 80th new hadron discovered at Large Hadron Collider experiments. It was also the first new particle discovered with the upgraded LHCb detector, a marker of what the improved instrument will likely continue producing as its dataset accumulates through Run 3 and beyond. The particle's predicted lifetime is significantly shorter than that of its doubly charged partner, despite their nearly identical masses. The difference traces to quantum interference effects in the decay process. The specific combination of quarks in the CCC+ allows decay pathways that partially cancel each other, shortening the window in which the particle can be observed. This kind of interference is a fingerprint of quantum mechanics operating at the level of the strong force, and measuring it precisely will constrain the theoretical models trying to describe doubly charmed baryon dynamics. Each resolved mystery opens adjacent questions. The doubly charmed baryon family is now confirmed to exist in 2 charged states, both matching theory. The next questions involve their internal dynamics, their decay pathways, and what they reveal about confinement in systems where 2 heavy quarks must share the force between them alongside a single light one. What all 80 hadrons together are revealing goes beyond any individual particle. Each new exotic hadron arrives with a mass, a decay width, a set of quantum numbers, and a challenge. The challenge is theoretical. Quantum chromodynamics, the theory of the strong force underlying every quark-based particle in the catalogue, is correct. Every test of its fundamental structure in regimes where the equations can be solved has confirmed it. The problem is that the regime where exotic hadrons form is precisely the regime where the equations resist analytical solution. The coupling constant of the strong force, the number measuring how strongly quarks and gluons interact, is large enough in this energy range that the standard method of building up a solution from small corrections fails entirely. The corrections are not small. They compete with the leading terms. The standard tools break down. Physicists use alternative approaches. Lattice quantum chromodynamics places the equations on a discrete space-time grid and solves them numerically using supercomputers. The approach works in principle and has produced impressive results for some quantities. For exotic hadrons, particularly the most complex configurations, even lattice methods strain under the computational demands. The particles are being found faster than the theory can keep pace, and the gap between experiment and calculation is exactly where physics makes its next leap. The mass of a newly discovered exotic hadron constrains every theoretical model attempting to describe strong force dynamics in complex quark systems. Its decay width narrows the range of allowed internal structures. Whether it appears to be a tightly bound 5-quark state or a loosely coupled hadronic molecule affects the models differently. Whether it decays predominantly through one channel or another encodes information about the quantum numbers of its constituents. The LHCb spokesperson Vincenzo Vagnoni summarized the situation after the March 2026 announcement. The results help theorists test models of how the strong force builds matter from quarks in all configurations, conventional and exotic alike. The experimental data and the theoretical models are locked in a dialogue, with each new particle narrowing the space of viable descriptions. Reflecting on the pace of discoveries in 2022, the LHCb physics coordinator drew an explicit comparison to the particle crisis of the 1950s. In that era, a cascade of unexpected new particles arriving from early accelerators convinced the field that an undiscovered layer of structure had to exist beneath them. The quark model eventually organized the chaos. The current cascade, arriving from a more powerful instrument and mapped in more precise detail, may be pointing at a similarly fundamental layer of understanding about how confinement actually operates in complex quark configurations. The zoo is a map. Each confirmed particle is a measured point in a territory the theory predicts must exist but cannot yet describe in full. The more points on the map, the better constrained the underlying physics becomes. What that map does not show is any sign of the new particles that would resolve the hierarchy problem. While LHCb fills in the strong force landscape, the detectors built specifically for the discovery of entirely new physics are reporting something very different, something they have not found. Atlas and the compact muon solenoid were built for exactly this moment, searching at the highest achievable energies for signatures of physics beyond the standard model. Both detectors have run for over a decade, processing collision data at rates that would have seemed impossible when they were designed, applying analysis techniques refined through years of experience, eliminating background processes with increasing precision. They have searched for dark matter across hundreds of distinct signal models. Dark matter makes up roughly 27% of the universe's total energy content. Galaxies rotate with a mass distribution that requires far more matter than visible stars and gas can account for. The geometry of gravitational lensing, the way light bends around massive objects, confirms the presence of invisible mass distributed on scales spanning millions of light-years. The structure of the cosmic microwave background, the oldest light observable in the universe, encodes the gravitational influence of dark matter in its pattern of temperature fluctuations. Every independent measurement points to the same conclusion. Something massive, invisible to electromagnetism, permeates the universe at a level 5 times greater than all visible matter combined. The standard model has no candidate for this role. One of the most promising strategies for finding dark matter at the collider is through the Higgs boson. If a dark matter particle exists and couples to the Higgs field, the Higgs could decay into a pair of dark matter particles that pass through the detector without leaving any signal. The signature would be a Higgs boson produced in the collision, identified through other decay products revealing its presence, and then an unexpected absence of energy where the dark matter particles escaped. This kind of result is called missing transverse energy. The collision debris should balance out in the plane, perpendicular to the beam. When it does not, something departed without being recorded. Both Atlas and the compact muon solenoid have searched for this imbalance across their full datasets. The current constraint excludes invisible Higgs decays above roughly 10 to 15% of all decays. Every excluded region is progress in one sense. In another, it is the tightening of a frame around something still invisible. The dark matter responsible for the structure of the observable universe remains completely undetected by the most powerful instruments ever aimed at the question. Searches extended further. Mediator particles, hypothetical objects that would carry the interaction between ordinary matter and dark matter. Long-lived particles that might decay only after traveling measurable distances inside the detector. Dark sector photons and dark sector Higgs bosons. Every model making predictions testable at collider energies has been tested. By the end of Run 3, no confirmed dark matter signal has appeared in any channel at any detector. 27% of the universe remains undetected, and while that search continues, there is something more immediate to consider about the particle that was found. The Higgs boson has now been measured with increasing precision across every accessible decay channel. The picture those measurements are building is one that physicists find deeply, specifically uncomfortable. Perfection is the result physicists would choose last. The Higgs boson has been measured for over a decade across decay channels ranging from the common to the extraordinarily rare. Every measurement returns the same answer. The Higgs matches the standard model's predictions exactly. Its mass sits at 125.09 billion electron volts. Its coupling to the top quark, to the bottom quark, to the W and Z bosons, to the tau lepton, all fall precisely where the theory places them. The pattern is consistent across both Atlas and the compact muon solenoid, across Run 1 and Run 2 and Run 3, across multiple independent analysis teams working on overlapping datasets. In July 2025, the Atlas collaboration presented new results at the European Physical Society conference. The analysis found evidence for the Higgs decaying into two muons, one of the rarest decay channels in the standard model. This particular decay occurs in roughly 1 in every 5,000 Higgs decays. It requires enough data and enough detector precision to observe a signal that represents a tiny fraction of an already rare process. The measured rate matched the standard model prediction. The collaboration also presented improved measurements of the Higgs decaying into a Z boson and a photon, a channel that proceeds through a quantum loop rather than a direct coupling. Particles too heavy to appear directly in collisions can still influence loop-mediated processes if they couple to the Higgs. A discrepancy in the rate would be a fingerprint of unknown particles contributing to the loop. There was no discrepancy. Every rare decay channel, every coupling strength, every production rate. The Higgs is cooperating completely with predictions written down before it was found. From one perspective, this is a triumph. The standard model makes extraordinarily precise predictions and the measurements confirm them. The theoretical framework has passed every test devised, including tests involving a particle that did not exist in any laboratory until 2012. The uncomfortable perspective is this: a Higgs boson deviating from standard model predictions would be a window. A different coupling strength, a missing decay rate, an excess in a rare channel, any of these would signal the presence of physics beyond the known framework. New particles coupling to the Higgs and altering its behavior. New interactions. New structure at higher energies. A hint. A perfectly standard model Higgs provides no hint. Its couplings carry no fingerprints of new particles. Its rare decays show no unexplained contributions. It reveals nothing that was not already known. And this matters because the Higgs mass is still 125 billion electron volts. The hierarchy problem is still unsolved. The fine-tuning of 34 decimal places has no explanation. The supersymmetric solution has no experimental support. The Higgs itself, measured with increasing precision, shows no sign of the physics that would resolve the problem. The number that haunts physics may simply be what it is: a fact without a mechanism, a value held in place by nothing visible. And there is a second number, equally precise, equally unexplained, that combines with the Higgs mass to determine something far more consequential than any particle discovery. That second number is the top quark mass, and it carries more weight than anything in the particle zoo. The top quark is the heaviest fundamental particle the standard model contains. Every other quark has a mass somewhere between a few million and a few thousand million electron volts. The top quark sits at 172.76 billion electron volts, nearly 200 times the mass of a proton. It was the last quark to be discovered, found at Fermilab in 1995, and its presence at such an extreme mass has always felt like an anomaly. Something at the far edge of the table, heavier than it has any reason to be. The top quark owes its mass to the Higgs field. Every massive particle couples to the Higgs, and the strength of that coupling determines how heavy the particle becomes. The top quark couples more strongly to the Higgs field than any other known particle. When physicists describe that coupling mathematically, the number they calculate is very close to 1, which in the language of quantum field theory means the interaction is as strong as it can plausibly be. The top quark and the Higgs field are bound together at the deepest level in a way no other particle in the standard model matches. That closeness has consequences. In quantum field theory, calculating how a particle behaves at high energies requires tracking how its interactions change as you probe finer and finer scales. The coupling constants shift. The self-coupling of the Higgs field, the parameter governing how the field interacts with itself, runs with energy according to equations that sum over contributions from every particle coupling to the Higgs. The top quark, because its coupling is so large, dominates this sum. It pulls the Higgs self-coupling downward as energy increases, harder and faster than any other particle. To understand why this matters, you need to know what the Higgs self-coupling actually controls. It determines the shape of the Higgs potential, the energy landscape that describes how much energy the field carries at different values. The self-coupling is, in a precise sense, the mathematical description of how stable our vacuum is. When it is large and positive, the field sits firmly at the bottom of a steep valley. As it decreases towards zero, the walls of the valley flatten. If it goes negative, the valley inverts. Another, deeper minimum opens up somewhere else in the landscape, and our vacuum becomes something other than the ground state of the universe. The measured mass of the Higgs boson at 125.09 billion electron volts, combined with the top quark mass at 172.76 billion electron volts, determines exactly how the Higgs self-coupling runs with energy. You feed the two numbers into the renormalization group equations and trace the self-coupling upward. Two independent analyses, one published in 2012 and one in 2013, traced that curve to its conclusion. Both reached the same point on the stability diagram. The top quark mass pushes the self-coupling down. The Higgs mass determines where it starts. Together, they place the universe in a region called the metastable zone. The calculations are clear. The measurements confirm them. And what those two numbers imply about the foundation beneath all of physics is the thing nobody in the field has been able to stop thinking about since the Higgs discovery was announced. What exactly metastability means is the next question. The answer requires understanding what the Higgs potential actually looks like. Picture the Higgs field as a landscape. Every point in space sits in this landscape, including the space inside your body right now. The field has a value at every one of those points, and that value corresponds to a position in the landscape. In our current universe, the Higgs field settled to a value of 246 billion electron volts everywhere in space, like water that has drained to the bottom of a valley and come to rest. That resting value is what physicists call the vacuum expectation value, and it is why particles have the masses they do. The field sits at the bottom of its valley, at the same depth everywhere in the observable universe. The walls of that valley are what keep the field in place. Steeper walls mean the field resists displacement more strongly. The self-coupling of the Higgs field is the parameter that describes how steep those walls are. When the self-coupling is large and positive, the valley is deep and stable. The field has no tendency to wander. Now take those renormalization group equations and follow the self-coupling upward through energies far beyond anything the Large Hadron Collider can reach. Go up by a factor of 1 billion from the collider's maximum energy. Keep going. At some point along that climb, which current calculations place at somewhere between 10 billion and 100 billion times the collider's maximum energy, it reaches zero. The walls of the valley go flat. Keep going further, and the self-coupling turns negative. When the self-coupling is negative, the Higgs potential no longer has a single stable minimum. A second minimum opens up at an enormous field value, far above the 246 billion electron volts our universe sits at. This second minimum is lower. The energy at that point in the landscape is less than the energy at our current vacuum. Our valley, the valley in which all of chemistry and biology and every structure in the universe exists, sits above a deeper one, separated from ours by an energy barrier of astronomical height. Yes. Inaccessible under normal conditions, yes, but present in the mathematics, supported by the measured masses, real in the sense that the equations and the data agree it is there. Our universe is sitting in a valley above the true minimum of the Higgs potential. The Higgs field, which permeates every cubic centimeter of space and makes atoms possible, is resting in a configuration that the laws of quantum mechanics say carries no guarantee of permanence. This does not mean the universe is about to collapse. The barrier between our vacuum and the deeper one is enormous. The probability of crossing it through normal thermal fluctuations is zero for any practical purpose. But quantum mechanics has a tool that ignores barriers. It is called tunneling, and it is the mechanism that makes the deeper valley reachable in principle, even when it should be unreachable in practice. That possibility has a name, and the name is something physicists have been careful to distinguish from the comfortable word stable. Our vacuum is metastable. The word has a precise meaning. A metastable state is one that sits at a local minimum, not the global minimum of its energy landscape. It is stable against small perturbations. A small push returns it to the same position. A large enough push, or a quantum tunneling event of the right magnitude, can displace it to the true minimum, where it will stay permanently. The universe has been in this state for 14 billion years. The Higgs field settled into its current value in the first tiny fraction of a second after the Big Bang, and nothing since then has displaced it. Every atom that has ever formed, every chemical reaction in the history of every star, every biological process in every living thing on every world, has occurred inside this metastable configuration of the Higgs field. The vacuum we inhabit is the only vacuum any of us, or any of our instruments, has ever experienced. Its stability is not in question on any human timescale. The lifetime of our vacuum, calculated from the measured masses of the Higgs boson and the top quark, exceeds any number that has a name in ordinary language. We will return to that calculation. But metastability is a categorical statement about the nature of our situation, independent of probabilities. We are in a local minimum. A global minimum exists. Quantum mechanics does not prohibit the transition. The barrier separating the two is what makes our vacuum persistent. In classical physics, a system sitting at a local minimum cannot cross a barrier. It would require an input of energy equal to the height of the barrier, and the barrier protecting our vacuum is orders of magnitude larger than anything accessible to any physical process in the current cold universe. Quantum mechanics introduces a different mechanism. A particle in a potential well does not need to go over the barrier. It can go through. The probability of tunneling decreases exponentially with both the height and width of the barrier, but it is never exactly zero. Given enough volume and enough time, a quantum fluctuation can nucleate a small region of field configuration that sits at the other side of the barrier. If that region is large enough, it becomes energetically favorable for it to grow. If it is too small, it collapses back into the false vacuum. The false vacuum is us. The true vacuum is what waits on the other side. What happens when the fluctuation is large enough is described in a mathematical framework worked out in the late 1970s and early 1980s, and the picture it presents has never been comfortably summarized or made any less unsettling by the decades of familiarity physicists have developed with it. The process begins with a bubble. Deep in the mathematics, of quantum field theory, there is a description of how a false vacuum ends. Physicists Sidney Coleman and Eric DeLucia worked out the process in 1980, building on earlier work by Coleman and Frank DeLucia on vacuum decay. Their calculation described what happens when a quantum fluctuation in a false vacuum is large enough to seed a bubble of true vacuum, a region where the Higgs field has tunneled through the barrier and settled to the lower minimum. They calculated the nucleation probability, the critical size required for the bubble to grow rather than collapse, and the dynamics of the expanding bubble wall after it exceeds that critical size. The result was published and read by physicists who found it theoretically interesting. It became practically interesting in 2012 when the Higgs boson was discovered at a specific mass and the calculation could be applied to the real universe for the first time. Here is what the mathematics says. Below the critical radius, a nucleated bubble of true vacuum is unstable. The surface tension of the bubble wall, the energy cost of maintaining a boundary between the two vacuum states, exceeds the energy gained by converting the interior to the lower state. The bubble collapses. The false vacuum reasserts itself. Nothing observable happens. Above the critical radius, the energy balance inverts. The volume of lower energy true vacuum inside the bubble grows faster than the surface energy of the wall. The bubble becomes energetically favorable to expand. It grows outward in all directions at the speed of light. The wall accelerates as the energy difference between the two vacua drives it forward. Within an instant on cosmic scales, the bubble is traveling as fast as anything can travel. Once a bubble exceeds the critical radius, no physical process can reverse it. The energy gain from expanding is larger than any conceivable force that could push the wall back inward. The universe cannot close the bubble. It cannot stop the expansion. The transition, once it crosses the threshold, is permanent and universal. The wall moves at the speed of light, and so does the region of altered physics behind it. Beyond the wall, in the old vacuum, everything continues as before. Inside the wall, the Higgs field has settled to its true minimum. The rules of physics in that region are permanently different from the rules in the region outside. The conversion of the observable universe to the true vacuum, if it began, would proceed at the speed of light outward from the nucleation point. Every part of the observable universe would be converted. There is no escape geometry. There is no location from which the bubble wall could be outrun. And there would be no warning. Light cannot outrun the bubble wall, because the bubble wall moves at the speed of light. The answer lies in physical causality. For you to receive any signal from an approaching boundary, that signal must travel from the boundary to you. A signal moving at the maximum possible speed, the speed of light through vacuum, would arrive at exactly the same moment as the boundary itself. A bubble wall traveling at the speed of light sends no advance notice. Whatever point the wall reaches, it reaches simultaneously with any signal that could have originated from it. The wall does not announce itself. It simply arrives. When it passes through a region of space, the Higgs field in that region shifts from its current value of 246 billion electron volts to the new, deeper minimum. The shift changes the underlying mathematical structure of the universe at that location. The mass of the electron, determined by how strongly the electron couples to the Higgs field, takes on a new value. The electromagnetic coupling shifts. The weak nuclear force, whose finite range depends entirely on the Higgs-acquired mass of the W and Z bosons, changes its character. The mathematical relationships that allow protons and electrons to bind into atoms, the relationships at the foundation of every chemical process that has ever occurred anywhere, no longer hold in the same form. Atoms do not explode. They do not burn or ionize in any conventional sense. The rules that define atoms change. Structures built on those rules dissolve because the rules beneath them are different. The process is instantaneous in the sense that matters. It happens as the wall arrives, at the speed that information travels. There is no experience of the transition from the perspective of any observer in the path of the wall. The question of what it would be like to encounter the bubble wall is answered by the same physics that makes the wall undetectable in advance. The relevant timescales are far below any biological or even atomic process. Outside the bubble, the universe continues. Stars, if any remain when the wall passes, continue burning. Planetary systems orbit their stars. The cosmic microwave background fills the sky as before. The expanding bubble is simply not visible from outside it, because the light from the conversion region is carried along with the expanding wall and does not precede it into undisturbed space. The bubble grows. The false vacuum retreats. The conversion is total and permanent wherever the wall has passed, and the probability of any of this happening has been calculated. Physicists calculated the lifetime of our vacuum, and the number is so large that communicating it requires some care. The calculation was performed by Dario Buttazzo and collaborators in 2013, using the measured values of the Higgs boson mass and the top quark mass that were available at the time. The method involved tracing the Higgs self-coupling from the electroweak scale up through energies where it turns negative, computing the nucleation probability per unit volume per unit time using the Coleman-de Lucia formalism, and integrating that probability over the accessible volume of the observable universe and the age of the universe to get a total decay probability. The result was a vacuum lifetime exceeding 10 to the 300th power years. 10 to the 300th power. Write out 10 followed by 300 zeros. That number has no name in any spoken language and no referent in any physical system. The total number of atoms in the observable universe is roughly 10 to the 80th power. The lifetime of our vacuum exceeds that number, raised to a power of nearly 4. The universe is approximately 14 billion years old, which is 10 to the approximately 10th power years. Our vacuum lifetime is longer than the age of the universe by a factor that is itself a number with hundreds of digits. Practically speaking, the universe is safe. The probability of a vacuum decay bubble forming anywhere in the observable universe in the next trillion years is so small that it could not be expressed as a fraction of any meaningful reference. On any timescale that involves life, or planets, or stars, or even the slow dimming of the last red dwarf stars billions of years from now, the metastability of our vacuum is irrelevant. And yet the word metastable remains. The calculation gives a finite number. The physics is not different in kind from a radioactive atom with a half-life of 1 trillion years, technically unstable, practically stable, but carrying within it the mechanism of its own transition. The mechanism exists. The true vacuum is there. The equations know about it. Measuring the Higgs mass and the top quark mass and running the calculation is the act of looking directly at the foundation of the universe and being told that the foundation is, in the most fundamental technical sense, resting on borrowed ground. There is a complication that the calculation did not include. It could not include it because the information does not yet exist. The Buttazzo calculation uses only standard model particles in the equations governing the running of the Higgs self-coupling. It assumes that no other particles exist above the energies currently accessible to experiment. If new particles exist, which all evidence suggests they do, those particles couple to the Higgs and alter the running of the self-coupling. The calculation of our vacuum's lifetime, the number on which our assessment of cosmic safety rests, is contingent on a set of particles that may be incomplete. Every unknown particle that couples to the Higgs field changes the calculation. The Higgs self-coupling does not run in isolation. It follows equations that track the contributions of every particle that interacts with the Higgs, summing their effects as the energy scale changes. Known particles are already in those equations. Their contributions are fixed by their measured masses and coupling strengths. The running of the self-coupling toward negative values at high energies is a consequence of the known particle content of the standard model, dominated by the top quark's large coupling. Unknown particles are not in those equations. They cannot be, because their masses and couplings are unknown. But if they exist, and if they couple to the Higgs, they contribute. Their contributions can push the self-coupling in either direction depending on whether the new particles are fermionic or bosonic, and how strongly they interact with the Higgs. Supersymmetry was, for 40 years, the primary theoretical argument for the stabilizing scenario. Every supersymmetric partner particle added to the equations contributes a correction with the opposite sign to its standard model counterpart. The superpartner of the top quark, the stop squark, would add a large positive contribution to the running of the Higgs self-coupling, partially counteracting the negative pull from the top quark itself. In the simplest supersymmetric models, the self-coupling remains positive at all accessible energies. Our vacuum is absolutely stable, and the hierarchy problem is solved by the same particles that secure the foundation. The Large Hadron Collider found no supersymmetric particles. The stop squark has been excluded up to masses well above the range where it would provide natural stabilization. The neutralinos and charginos and gluinos that should have appeared have not. The particles that would have both explained the Higgs mass and secured the vacuum are absent. Other unknown particles, of different kinds, could destabilize the vacuum further. Some theoretical extensions of the standard model introduce new heavy particles that couple to the Higgs with large negative contributions, driving the self-coupling to zero at lower energies than the standard model alone predicts. If such particles exist, our vacuum lifetime is shorter than the Butazzo calculation estimates. The floor shifts downward. The reassuring number with 300 zeros in it gives way to something smaller, though still enormous by any human measure. The troubling realization is symmetric. The particles that could be protecting the vacuum are the same ones the collider has been unable to find, and the particles that could be shortening its lifetime are equally invisible. Both possibilities are permitted by everything currently known. Resolving the uncertainty requires either finding new particles or constraining them further. The High Luminosity Large Hadron Collider upgrade will tighten the constraints. But there is a range of masses and coupling strengths that may never be directly testable at any particle collider within reach, which means the vacuum stability calculation may remain contingent on unknowns for generations. There is a deeper version of this uncertainty, one that ties the vacuum stability calculation to a question the standard model has never answered: why the Higgs mass sits at this specific value in the first place. If the Higgs mass were higher, the vacuum would be safe. This is a mathematical fact, not a preference. The running of the Higgs self-coupling depends on the value of the self-coupling at the electroweak scale, which is set by the Higgs mass. A heavier Higgs starts the self-coupling at a larger positive value. The top quark's downward pull still operates, but the self-coupling has more ground to lose before reaching zero. For a Higgs mass of roughly 170 billion electron volts or above, the self-coupling never turns negative within any energy range expected to be physically relevant. Our vacuum would be absolutely stable. The second minimum would not exist. The foundation would be permanent. If the Higgs mass were significantly lower, the universe would have ended long ago. A lighter Higgs starts the self-coupling at a smaller value, and the top quark's coupling would drive it negative at much lower energies. The second minimum would appear at accessible scales. The vacuum decay rate would be fast enough that a bubble would have nucleated somewhere in the observable universe within the first billion years of its existence. The universe we see, 14 billion years of structure and complexity, would not have had time to develop. The measured Higgs mass of 125.09 billion electron volts falls between these two outcomes. It is above the threshold of rapid instability. It is below the threshold of absolute stability. It lands in the narrow band where the vacuum is metastable, stable enough to persist for a time that makes the word lifetime almost meaningless in practice, but categorically impermanent in principle. The width of this metastable band, when plotted against the axes of Higgs mass and top quark mass, is narrow. Small shifts in either measured value move the point out of the metastable zone and into one of the adjacent regions. The precision of the placement has no explanation in the standard model. The theory that contains the Higgs boson does not predict its mass. It predicts that a Higgs boson exists and requires some mass value, but the specific number must be measured and inserted by hand. The standard model offers no reason why the value is 125 rather than 150 or 80 or 10,000. It simply is. The thing that makes our existence possible and the thing that makes our existence impermanent are the same number. The Higgs mass that gives electrons enough mass for atoms to form is the same Higgs mass that places the vacuum in the metastable zone. The load-bearing structure of chemistry and the contingency of the vacuum are both expressions of a single value that the most precisely tested theory in science cannot explain. Some physicists have called this a coincidence. Others have proposed that it is a signature, an effect pointing toward a mechanism that drives the universe toward exactly this edge. A 2024 paper published in Physical Review D proposed that the universe may have been pushed here. The researchers, working at King's College London, described a model in which an axion-like particle coupled to the Higgs field could, through cosmological evolution, drive the effective Higgs potential toward the near-critical boundary between stability and instability. The mechanism is dynamic, driven by the universe's own history rather than any imposed adjustment. The universe's history, the evolution of the fields present during and after the Big Bang, moves the Higgs toward metastability as a consequence of how the coupled system behaves over time. Axion-like particles are a class of hypothetical light scalar fields that appear in many extensions of the standard model. The original axion was proposed in the 1970s to address a separate puzzle in quantum chromodynamics. The theory of the strong force permits a term in its equations that would cause large violations of charge parity symmetry. But measurements show this violation is essentially zero. The Peccei-Quinn mechanism introduced a new field that dynamically cancels the offending term, predicting a new light particle as a consequence. That particle, the axion, is also a candidate for dark matter. The King's College London model extends this idea. An axion-like particle coupled to the Higgs field does not merely solve a different problem, it shapes the Higgs potential over cosmic time. As the universe expands and cools, the coupled system evolves. The effective value of the Higgs self-coupling, the parameter governing the shape of the energy landscape, is driven toward the critical boundary. The universe is drawn toward metastability. If this mechanism operates, the placement of our vacuum precisely at the edge of stability reflects the universe's own dynamics rather than an unexplained accident. The existential situation does not become less unsettling for having an explanation. The lower valley is still there. The bubble nucleation probability is still finite. The vacuum is still metastable. But the question of why the Higgs sits where it does would have an answer. The model makes testable predictions. The signatures it predicts appear in an energy range spanning from a few million to 10 billion electron volts, a range that several experiments currently operating or under construction can probe. The axion-like particle itself, if it exists with the properties required by the mechanism, would leave specific decay signatures detectable at collider experiments and beam dump facilities. Those facilities are now being built. The last act of the Large Hadron Collider program is beginning. Late in 2026, the Large Hadron Collider will shut down for the most significant upgrade in its history. The machine will go quiet. The superconducting magnet system will be warmed, slowly, from its operating temperature of -271 degrees Celsius toward ambient. The tunnels, which have carried 2 beams of protons around a 27-kilometer ring for over a decade and a half, will sit empty while engineers install new magnets, new focusing systems, and upgraded detector components at the 4 collision points. The process will take approximately 4 years. When the collider restarts as the High Luminosity Large Hadron Collider in 2030, it will be a fundamentally different instrument. Stronger magnets will focus the proton beams into smaller cross-sections at the collision points, increasing the probability of proton-proton interactions at each crossing. The upgraded machine will deliver roughly 5 times more collisions per year than the highest luminosity achieved in Run 3. The datasets that physicists will work with after 2030 will dwarf everything collected in the previous 2 decades of operation. What those datasets will enable is the direct measurement of the Higgs boson's coupling to itself, the self-coupling parameter that governs the shape of the Higgs potential and appears in every vacuum stability calculation. No previous experiment has been able to measure this quantity. It requires observing 2 Higgs bosons produced simultaneously in a single collision, a process so rare that even the record-breaking Run 3 luminosity produced only a handful of candidate events. The High Luminosity Large Hadron Collider will produce enough of them to make a measurement. That measurement will sharpen the vacuum stability calculation in a way no previous result has managed. The self-coupling at the electroweak scale is the starting point for tracing the Higgs potential to high energies. Knowing it precisely means knowing where the walls of our valley begin. The SHIP experiment, a beam dump facility approved at CERN in 2024 and scheduled for operation around 2031, will search for the axion-like particles predicted by the King's College London mechanism. Rather than colliding beams of protons, the SHIP experiment fires a high-intensity proton beam into a fixed target and searches for rare particles produced in the resulting interactions, looking far downstream for the signatures of long-lived hidden sector particles that would be invisible to conventional detectors. 2 outcomes are possible when the High Luminosity Large Hadron Collider finishes its program. In the first outcome, new physics appears. A supersymmetric particle at higher mass, an anomaly in the Higgs, self-coupling pointing to unknown structure, a signal at SHIP matching the predicted properties of the axion-like particle. Any of these would open a door. In the second outcome, nothing new appears. The Higgs self-coupling is measured and matches the standard model. The hierarchy problem remains unsolved. Supersymmetric particles remain absent up to the highest energies the upgraded machine can reach. The metastability of our vacuum stands unresolved, with no known mechanism and no detectable solution. The scaffolding is confirmed to be exactly where it is, holding everything together, resting on a foundation that the best physics humanity has ever built cannot explain. The second outcome may be the more disturbing result. We already have the answer. It has been sitting in 2 numbers since July 2012. The Higgs mass at 125.09 billion electron volts. The top quark mass at 172.76 billion electron volts. Feed them into the renormalization group equations. Trace the Higgs self-coupling upward through energies the Large Hadron Collider will never reach. Watch the self-coupling decrease. Watch it reach 0. Watch it turn negative. The second minimum is there. Every precision measurement made since the Higgs discovery has confirmed this picture rather than complicated it. The exotic hadrons catalogued by the LHCb detector, all 80 of them, demonstrate that the strong force is richer and stranger than the simplest models described, but they do not shift the vacuum stability calculation. The search for supersymmetric particles has returned silence across every accessible energy range, leaving the hierarchy problem unresolved and the particles that might stabilize the vacuum absent. The dark matter, comprising 27% of the energy content of the universe, has evaded every detector aimed at it, remaining as invisible now as it was before the Large Hadron Collider began running. The Higgs boson itself has been measured in every accessible decay channel, and it matches the standard model in each one with a precision that forecloses almost every proposed window to new physics below the current energy frontier. The machine built in a ring of tunnels buried 100 meters below the ground, straddling two countries, colder than the emptiest regions of space, smashing matter together at conditions that existed in the first instance after the Big Bang, has been running for 15 years. It found the Higgs boson. It confirmed the standard model to a level of precision that no previous instrument approached. It discovered 80 new hadrons, revealed the strong force operating in configurations physicists had theorized for 6 decades, and mapped the boundaries of what the known particles can build. And then it measured the Higgs mass and the top quark mass, and the combination of those two numbers told a story that the discovery itself had made impossible to ignore. CERN built the most precise instrument in human history to find what holds the universe together. It found the Higgs field, the actual load-bearing structure beneath all of chemistry, beneath every atom in every living thing, beneath every star and every galaxy cluster and every photon that has crossed the observable universe since hydrogen first formed. The field is real. It permeates every point in space. It gives electrons their mass and makes atoms possible. It is the reason anything complex exists at all. And then, the measurement of that field revealed something else. The load-bearing structure is real. The Higgs field holds everything together. But the field is resting in a configuration the equations recognize as temporary. A deeper state waits beyond it, separated by a barrier of extraordinary height, and quantum mechanics does not prohibit the transition. Somewhere in the fabric of the universe, at some point in space and at some moment in time, a fluctuation could nucleate a region where the field has already made the transition. That region would expand outward at the speed of light, permanently and without reversal, carrying different physics in its wake. The probability is vanishingly small on any timescale a human being can hold in their mind. The universe is safe in any meaningful practical sense, but the hidden structure is there. The scaffolding is real. The lower valley is waiting in the mathematics. And the machine that found all of this, the machine that told us the universe is held together by a field resting in a state that is technically temporary, is about to be upgraded to see further still. The answer has not changed since 2012. The numbers say what they say. The only question left open is whether anything in the universe knows something the standard model does not, and whether whatever that thing is will show itself to the next instrument before the instruments run out. We have been building machines to ask the deepest question physics contains. The question is no longer whether the hidden structure exists. We know it exists. We have measured it. The question now is whether it will hold.